Hello everyone, welcome to our presentation on Mechanism Sessional Tutorial 5 where we will discussing the Windscreen Wiper mechanism. I am Saloni, roll number 23ME10074 and I am joined by my teammates Raksha Gupta 23ME10066, Rupali 23ME10070 and Sritoma Nandan 23ME10104. In this video we will take you through our complete process from theoretical background and simulation to analysis and real-world application. Although we see wipers every day on vehicles, they are an amazing example of how a smart mechanism design makes everyday life easier.
The objective of this tutorial was to synthesize and simulate a windscreen wiper mechanism based on the problem provided in our tutorial sheet. Our main challenge was to design a wiper mechanism without any quick return effect, meaning it should move symmetrically in both directions, maintaining equal timing for forward and backward motion. We were also required to create a simulation where we used MotionGen software to visualize how the wiper moves and to mark the wiped area on the screen. Apart from that, we included additional features like providing adjustment provisions to change or increase the wiped region and analyzing the variation of velocity and acceleration of the wiper for a given constant motor speed. So overall, this project involved both theoretical kinematic analysis and practical simulation-based understanding.
To complete the project in a structured way, we first set a series of clear goals. Selecting the mechanism type. Usually a 4-bar linkage or a crank rocker mechanism is ideal for wiper systems. Synthesizing and iterating the design to achieve the desired range of motion. Simulating the wiper movement in MotionGen to verify motion. Marketing and determining the wiped area through displacement analysis. Performing velocity and acceleration analysis to study the dynamic behavior of the system. And finally, optimizing the design for efficient and smooth operation. This systematic process ensured that we covered both theory and simulation aspects properly.
Before moving into simulation, we study the theoretical background, mainly focusing on the Grashof condition. As we all know, according to the Grashof criteria, the sum of the shortest and the longest link in a 4-bar mechanism should be less than or equal to sum of the other two links. When this condition is satisfied, the mechanism is said to be the Grashof mechanism, meaning one of its link, the crank, can make a complete revolution. In our mechanism, the link AO2 is the shortest link and therefore it acts as a crank. It rotates continuously, driving the other links to create an oscillating motion at the wiper arm. This satisfies the Grashof condition and ensures smooth continuous motion of wiper blade.
Once the design parameters satisfied the Grashof condition, we implemented the mechanism in MotionGen software. In the simulation, we could clearly see the crank link AO2 performing a full rotation and the wiper link oscillating smoothly like a real wiper. We then experimented with a few variables. First, we changed the RPM from 30 to 15, and then now we can see that the wiping speed reduced proportionally. Then we can also change the crank length AO2 and notice that it affected the wiped area. Increasing the crank length increased the sweep area. However, when we violated the Grashof condition, that is when the crank was no longer the shortest link, the mechanism stopped working properly. The crank could no longer complete its revolution and the system locked. This demonstrated the practical importance of Grashof's law in real mechanism design.
So next comes displacement analysis, which help us understand the exact angular position of the wiper for any given crank angle. We used complex number analysis for this. By representing the linkage geometry mathematically and assigning one joint as the origin, we found the coordinates of other joints and calculated the output angle, that is theta 4, and corresponding to each input angle, that is theta 2. For our setup, the linkage connected to the wiper was 30 cm long and the coupler linkage length was 50 cm, divided as a 7.5 cm on each side. Based on this value, we calculated the start and end position of the wiper sweep, and from that we determined the wiped area, which come out to be approximately 15.171 square centimeter. This value was then verified through simulation and matched our analytical result.
After finding displacement, we analyzed the velocity of different link. We used the instantaneous center IC method based on Kendall theorem, which states that when three bodies move relatively to one another, their instantaneous center lies on a straight line. We identified the centers I12, I23, I34 and I14 for our mechanism. Using this and then given motor speed, we determined angular velocity of output link theta 4. In our analysis, we assumed crank speed 30 rpm, crank length 30 mm and compute other link length accordingly. We then plot angular velocity versus time using Python. The graph shown that wiper velocity increased during the middle of the sweep and decreased near the reversal point. This is exact what we observe in real wiper. They slow down slightly before changing direction. After velocity, we perform acceleration analysis to understand how quickly the wiper speed change over the time. Since we already had expression for angular velocity, we differentiate it to get angular acceleration. This was done easily using Python NumPy gradient function. The acceleration versus time plot shows clear peak at the turning points where the wiper stop and reverse direction. This analysis is very important as high acceleration can lead to mechanical stress, joint wears and uneven wiping. By observing this result, we could understand how link dimension and motor speed influence smoothness of motion.
The wiper mechanism is a real-world necessity and has many practical uses beyond just car, like motor vehicles found in cars, trucks and buses for clearing rain and dust for windshields. Marine vessels used on ships and boats to remove salt spray and rain, ensuring visibility during navigation. Solar panels. Wiper systems are used to remove dust and dirt from solar panels, especially in dry regions prone to dust storms. Autonomous robots used for keeping cameras and sensors clean in a dusty and wet environments. Meteorological devices installed on a weather instruments to clear snow or rain from sensor surface for accurate readings.
Future innovations. In the future, wiper systems are becoming more intelligent and automated. Some of the modern advancements include rain intensity sensors, which automatically adjust the wiper speed based on rainfall intensity. The dynamic coverage system to detect unclean areas and focus wiping there using sensors. Weather integrated control that sync wiper motion with the real time weather data anticipating rain or snow. And last, electrostatic wipers that use electric fields to repel dust, dirt, and water, keeping the windshield clean without physical contact. These developments are taking a simple mechanical mechanism and transforming it into a smart mechatronic system. This brings us to the end of the presentation, to conclude which we can say that the windscreen wiper mechanism perfectly combines theoretical kinematics and practical design. Through this project, we learned how to apply Grashoff's law, perform link synthesis, run simulations, and analyze velocity and acceleration both mathematically and computationally using Python. We also understood how design parameters affect motion smoothness and wiped coverage area. Lessons that are directly applicable in automotive and robotic design. We'd like to sincerely thank our Professor Anirban Das Gupta for guiding us through this and helping us explore mechanical systems in depth. Thank you.